Okay, so I call this I call this problem right here the Mississippi problem. Um and I feel like if I don't do the Mississippi problem, then you might not understand what I'm doing. So I'm going to come back and do these two right here are both examples of the Mississippi problem, but I really feel like I need to do the Mississippi problem. So let me go over here and we'll do Missississi PPI. Okay, so the first thing that I need to do for the Mississippi problem is I need to count the total number of things that I have. It doesn't matter whether they are distinguishable or not. You count them all. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So for this problem, my number of items or objects are 11. The problem is those 11 items are not distinguishable. So what I need to do now is go, not all 11, I can't, in other words, if I said this before, but if I had these Scrabble tiles and I picked a Scrabble tile out of a bag, would I be able to tell the difference between the Scrabble tile that I used for that eye and that eye and that eye and that eye? Would I be able to tell the difference between those eyes? No, I wouldn't know which one it was. Unless, of course, I marked the back of that or something. But just looking at the Scrabble tile by itself, I wouldn't be able to tell. So the indistinguishable things that I need right here are going to be eyes. Well, how many eyes do I have? 1, 2, 3, 4. I have 4 eyes. And then for S's, those are also indistinguishable. 1, 2, 3, 4. I have 4 of those. And then I have P's. Those are indistinguishable. And I have 2 of those. And then the M, I just have 1 of those. So it's distinguishable from all the others. So these are the indistinguishable items or objects that I have. So the way this works is I do 11 factorial on top, and I'm looking at this formula right here. Do the total number of objects that you have, factorial on top. So I'm going to do 11 factorial, and then I'm going to divide out the ones that are indistinguishable. So 4 factorial times 4 factorial times 2 factorial. Divide those out. So if I used the Desmos calculator, which is my favorite, because it has that nice fraction bar, go back to the main menu. There's my fraction bar. And then do 11 factorial on top, and then divide it by 4 factorial. And I don't know if you have to do times or if times implied. I'm going to go ahead and put the times button just in case leaving it out would mess it up. 4 factorial and then times, and then we do 2 factorial. And that gives you the total number of ways to arrange the letters in Mississippi that are distinguishable from one another. So 34,650. So 34,650. Now, what I want to make sure that you're understanding, I'm claiming that this is one arrangement of those letters, and now I'm claiming that this is a second arrangement of those letters. I've rearranged something. Can you tell what I've rearranged? No, you cannot. Well, what I rearranged is I really moved the I's. That's what I moved. I switched those I's. Or I don't know, maybe I switched the P's. But you can't tell the difference in the word. So since you can't tell the difference in the word, we don't get to count that one as a new arrangement. So I'm going to go down here, and now I'm going to say that here's a different arrangement. Can you see the arrangement, the rearrangement that I made? Yes, you can see I rearranged, I put the I first and I put the M second, and then I left everything else the same. So this is a different arrangement of these letters, and I can see it. So when I counted this count right here, this count, which is equal to this right here, this is only counting these rearrangements that I can visually tell the difference between. So if I now go back and say this is a third arrangement, because somebody might say, you know, try to say this. Well, there's a new arrangement, and I'm arguing, no, it's not. And you say, yes, it is. I switched those two P's. I put this P first and I put that P second. I still wouldn't count that one because I can't visually tell the difference. So I want to make sure you understand that's what I'm talking about when I say distinguishable arrangements. That's what I mean. I can see the difference. All right, so I'm going to go back over here now, and it says use the formula for distinguishable permutations. Using the formula for you can determine the number of distinguishable permutations for these letters. Okay, so first thing we do is give me a count, a total count. 1, 2, 3, 4, 5, 6, 7. So N is 7. And then I'm going to count the repeats. This is what I count, the repeats. 1, 2, 3, 4. I have 4 A's, and then I have 2 B's. So those are all of my repeats. So the final answer then can be calculated by doing 7 factorial divided by 4 factorial divided by 2 factorial. And then run to the calculator and calculate that. And that's 7 factorial divided by 4 factorial times 2 factorial. And the answer is 105. So there's 105 ways for me to take these letters and be able to see a distinguishable rearrangement. There's 105 of them. A building contractor is planning to develop a subdivision. The subdivision is to consist of 6 one-story houses, 4 two-story houses, and 2 split-level houses. How many distinguishable ways? Now, this is kind of contrived. I feel like they're forcing a word problem here because I live in a subdivision that has the same floor plan used over and over and over. The house right across the street from mine is exactly like mine, but you can tell the difference because they use different brick. So here we have to pretend, in order for this problem to fit this problem right here, we have to pretend that all 6 of these one-story houses are painted or bricked identically. Okay, so there's no difference between them. And you also have to imagine that we can pick one up and move it around. So maybe what we should do is pretend that this is a planning board. You know how when you're planning a subdivision, they have those little Monopoly pieces. This makes more sense. I've got 6 one-story houses in my Monopoly pieces. I've got 4 two-story houses, and then I've got 2 houses that have part of it's 2-story and part of it is 1-story. That's what they mean by split level. So think of Monopoly pieces here. That makes this question a little bit more understandable. I don't like when they force a word problem into an example. It's usually terrible and disastrous. So the total number of houses, I've got 6 and 4, 10. So I've got a total of 12 houses in this subdivision. But the 1-story houses, the repeats, that's what I'm counting. So 1-story, how many of those are there? There's 6. And then I've got 2 stories. Why do you think they call them stories? I don't know. And then the split level, I have 2 of those. So these are my repeats. All right. So to figure out how many different ways I could arrange these different types of houses, I do 12 factorial on top and then divide out the repeats. 6 factorial divided by 4 factorial divided by 2 factorial. And then go to your calculator and work that out. Give yourself a fraction bar. 12 factorial over 6 factorial times 4 factorial times 2 factorial. So 12 houses altogether, 6 one-story, 4 two-story, and 2 split level. When you type that in, you get 13,860 different ways to arrange those 12 houses. 13,860. So that's equal to 13,860. All right. Let's see. All right, so these last two problems are examples of combinations. And again, the reason that they're combinations is because order doesn't matter. So the state's Department of Transportation plans to develop a new section of interstate highway and receive 16 bids for the project. The state plans on hiring 4 of those bidding companies. So the fact that I'm choosing 4 out of the 16, okay, so that's really easy. We still do, how many things do we have to pick from? We have 16. How many of them are we choosing? We're choosing 4. That's going to be the same whether it's a permutation or combination. But now I have to ask myself, does order matter? So if these 4 that I'm hiring, if I hired you first, are you going to get any advantages to being hired second compared to the one hired third compared to the one that's hired fourth? Not in this word problem. I'm not seeing any advantages. So there's not a first place bid, a second place bid, a third place bid. It doesn't say that. It just says I'm going to pick 4 of those bids. And because there's no advantage to being hired in any particular order, order does not matter. Order not matter. I just have 16 things. I'm going to pick 4 of them. And it doesn't matter whether I picked, company A first or company B first. There's no advantage to being picked first. As a matter of fact, I may just throw all 16 of them in a hat and reach in and grab 4 all at the same time. That's another example of order not mattering. I can pull 4 of them out at the same time because it doesn't matter. There's no distinguishing marks or there's no distinguishing characteristics between being picked first versus being picked fourth. So since order does not matter, it's a combination. So I'm going to do 16, choose 4, where order doesn't matter. And the formula says it's almost just like the other one. I'm going to do 16 factorial on top. And I still do 16 minus 4. I still do that. That's this part right here, n minus 4. I still do 16 minus 4. That's 12 factorial. But then I multiply or divide out some more because of order not mattering. So this divides out the fact that my order doesn't matter. So now you go do that calculation. 16 factorial over 12 factorial times 4 factorial. And the easy way to remember this one is that these 2 numbers on the bottom should add up to be that one. So this is always going to be your R. So whatever that number is, your R, we're choosing 4 companies. So that means that we also have to divide out the 12 because these 2 should add together. Okay, so 1,820. The answers to combinations are always going to be smaller than the answers to permutations. 1,820. 1,820 different possible combinations of those 16 companies, of choosing 4 at a time. A student advisory board consists of 17 members. There's my total number of objects. I've got 17 members. 3 members will be chosen to serve as the board's chair, secretary, and webmaster. So since these are named, then order does matter. Oh, I'm choosing 3. Let me go back and put this. Since they're named, then it does matter. Because the person that, if I say Abigail's going to be the board's chair, and Jeffrey is going to be the secretary, and Jesus is going to be the webmaster, that's a different arrangement than if I say Jesus is going to be the board's chair, Abigail's going to be the secretary, and I don't remember, Jeffrey is going to be the webmaster. That's 2 different arrangements. So since these are ordered, this is order does matter. And since order does matter, then this is 17 choose 3 with a permutation. And that's just 17 factorial over 14 factorial. 17 minus 3. So the combinations here, let me give you some examples of combinations. Well, let me do this first. 17 factorial over 14 factorial. 17 factorial over 14 factorial. So 4,080. So this would be 4,080. Now, let me give you some examples of combinations. A banana split. So you go to the store and you get a banana split, and there are, I don't know, let's say 6 flavors of ice cream to choose from. So the banana split there's 6, what did I say, 6 flavors of ice cream. And you're going to choose, the banana split allows for 3. Okay, you can get 3 scoops. Well, do you have the same banana split if this is chocolate, this is vanilla, and this is strawberry, versus this one being vanilla, this one being chocolate, and this one being strawberry? Is that the same banana split? Yes, because the fact that they're in a different order doesn't mean that you have a different, the order in which the ice cream is served doesn't matter. I mean, because if I flipped the container around, that would give me a different order, and it's still the same banana split. So when we're talking about food combinations, generally the order in which they're served doesn't matter. Okay, so this would be an example of a combination. This 17 student advisory, if I didn't name those, if I just said I need a 3-person committee, I'm just going to pick 3 people to represent. They don't have titles. They're just going to serve together as, that's a combination. A 3-person committee. I don't know how to spell committee. So a 3-person committee from 17 members. That's a combination problem. That's a 17 choose 3 for a combination. This would be 6 choose 3. This would be 17 choose 3. Let's say I'm going to go on vacation and I own 10 books. I have 10 books at home, but I can only fit 3 of them in my bag. And I just choose 3 books and I throw them in my bag. that is an example of a combination. Why? Because I didn't say I'm going to read this one first, this one second, this one third. I'm not placing them on a shelf. I'm just throwing them in a bag. The bag is not arranging them. They're going to get jostled around. I don't care, which one I read first. I'm just going to stick my hand in the bag and pull a book out. So if I have, 10 books and I choose 3 of them, I keep using the same number 3. And I'm just going to throw them in a bag and take them on vacation, then order doesn't matter. Now, if I have 15 books and I'm going to place those 15 books on a shelf, then order does matter, because the arrangement on the shelf can change based on which one I put first, which one I put second, which one I put third. That's arranging them on a shelf. Order does matter. If I rearrange the books, it's a different order. But if I'm just throwing them in a bag, order doesn't matter there. And yes, it just takes experience to read these problems. And even I mess up. I missed this banana split one because I teach this in geometry. And I miss this banana split question every single time we give it, because I do it as a permutation and not a combination. So don't feel bad if you struggle to figure out which one it is. I will try my very best to make it very clear and plain whenever you're taking a test what kind of problem it is. So be sure you pay attention. Ask me questions if you have any. I think that's the end of this super, super long lesson. So good luck. I can't even figure out how to turn this recording off.